those online, are you able to hear my voice? Thank you. So, sound is okay. Just the recording failed last, and so I haven't uploaded lecture 18 video recording. I captured it now, so it seems to be capturing the audio. It captured the video, but it didn't capture the synchronized audio part. Okay, good morning. We'll just get started, even though there are only a few people here. 5 online, and 3 people from PI are there. That's good. What I wanted to do today, I guess, is just take a few minutes to lay out the expectation for the assessment part, because we are reaching the tail end of the course. We have exactly 8 lectures left. So I have a lot of things I want to cover, but I also want to set up the procedure for what we are going to do for assessment. So I have given some guideline here for timelines. I don't know whether you've seen it and you're following it. Only 3 people have kind of submitted a preliminary report on literature search, which I had suggested by around April 1st. But it's not mandatory, and I'm not going to assess that part, just to make sure that you are following roughly some sort of a timeline so that you don't crash into this in the last week. But those who have provided report, I will provide some feedback within a couple of days. And right now, according to the schedule, you should be in the middle of doing some simulations and validations. But that may not be happening. That again is a soft deadline. Conduct parametric studies over 10-day period. That's again a suggestion only. Write the final report from 20th to May 2nd. I have given you some leeway there. The hard deadlines are in red. Again, that's what I want to focus on, because I have a deadline to report marks, grades for this course, and I may have 2 different deadlines, one for the PI and one for SU. So this is for LSU. So for PI guys, I'm willing to listen to your schedule and alter it for what I'm suggesting. But May 5th, the Sunday, we'll have a kind of a mini conference, and each student will present for about 20 minutes on their project work. Okay, so it's a 15 to 18 minute presentation followed by 2 to 3 minute question and answer discussion. So it'll be whole day. And for lunch, I will provide the pizza for here. For PI guys, of course, it'll be midnight, so you'll be probably sleeping. So what I suggested is all LSE students are expected to be present for all the presentations, but PA students are excused after their group finishes. So I'm going to schedule them first. So once you make your presentation, and we need to test this out to make sure that it works for you guys from time. So that's May 5th. Okay, keep that date. And then the other hard deadline is May 10th. So instead of May 2nd, May 10th, Friday, 4 p.m., I will create a submission portal for in Moodle for you to submit the final report. The final report should be in electronic form, so Word or PDF file, and at least one COMSOL simulation file that you have to provide. Okay, if you use COMSOL, if you use something else, then provide whatever that tool that you used, the software that you must create some sort of an input file for software. I would like to take a look at that. So that's a hard deadline. Okay, I need that by so that I can go over them that night. And next day is your oral exam. It's a Saturday, last day of exam at LSU. Okay, so that's a hard deadline for me. I need to finish by that day. So I'm really giving you all the time that you need till the very last day. And I need to submit the grade within a few days after that. Okay. So the individual oral exams, each 30 minutes, and to be scheduled in alphabetical order starting at 9 a.m. And PI guys go first, and then the LSU guys, in each case alphabetical order. And If the PIV exam period is different and you want to fill it at a different time, I'm willing to listen to that. So this is just a suggestion for you guys. But LSU, we need to submit a grade soon after that. So that will be a hard deadline. And note on the exam format so that you know what to expect. I'm hoping Mrinal will be here, and maybe I will have the TAU also. So it will be 3 people in the examining committee, if you like. So it's like a mini final defense. So I'm proposing that I will have 250. Each exam is going to be 30 minutes in duration. Okay? And you just have to come for your exam and you can leave. Okay? So you can schedule that day. You don't have to be there the whole day. And I'll show you the schedule next. 15 minutes will be on the course content, 15 minutes focused on your project. That's why I need your presentation and the report due method. And it's essentially to see whether you can engage in a meaningful discussion. I'm not going to say derive Rankakada method, 4th order method in 10 minutes. Okay, so just to engage you in an intelligent, meaningful conversation, and defend the choices that you made in COMSOL or whatever software that you use. Discuss the results from that. So in the later part of the 15 minutes, in the first part of the 15 minutes, I will focus on what your question. I'll focus on the box that I put at the beginning of each lecture, which is a recap of the previous lecture. Okay, so it highlights all the important points that you should have attained from the previous lecture. So you should be familiar to be able to discuss anything in that. Okay. And note on the report, as it should not exceed 25 pages, including no more than 1 page for bibliography. I'm expecting you to find 9 other related papers. Identify 1 key paper that you are going to simulate to produce the result. All, including all tables and figures, can be single space, 12 point. These are all the rules that we are given, right, when you're writing a proposal and things like that. So that you don't cram too many things inside that. And the key part is it should be structured like a research paper that you are reading. So it should have an introduction section, a literature review, model formulation, numerical validation. Of course, I'm left with the abstract. I should probably put the abstract there also. So that's the kind of expectation that I have. Do you have any questions? If not, this is the tentative schedule I'm proposing. So just alphabetical order, and I will put this up on Monday. 20 minutes for presentation with a 1 break on that week. So the last presentation in the morning will be 11:40, and then from 12 to 1 we'll break, and then we'll resume from 1 o'clock onwards. But the first 4 are the PA students, and it will be getting late for you by that time. So after your presentation is when you can leave. The presentation will be done using Adobe. So if you want to send us the PowerPoint presentation ahead of time, it's not a bad idea. But you can also, I can make you as the host, and you'll be able to drive the connect from your desk. But please make sure that you have a good mic, because we need to be able to hear your presentation. So all of you can be just in front of one computer if you like, but make sure that it is equipped with a good mic for your presentation. Okay, any questions? And the exam, it's just going to be a hard day for the 3 of us. We're just going right from 9 till 5:30 or so without a break. But you have to appear before your time slot. Okay. Any questions from guys at 9? We have classes on that day. Okay. So if you have conflicts or classes, I am willing to reschedule on which day? On the presentation or on the oral exam day? Yeah, the classes start on the day, that's right. presentation. Okay. All right. We will communicate offline with the four of you to see whether we can schedule a presentation at another suitable time. You guys come up with a well, the oral exam will be in the class here and the classroom, but for PI people it will be online. Okay. Okay, so the oral exam is fine, just the presentation. We will try to reschedule that to a different date. And we can do it even after. The hard deadline is only for LS. You guys don't need to submit the grade. But there will be a similar hard deadline at the PI where I have to submit your grades there. Okay, so I need to know what that is. And then we can work around that. Okay, so we will communicate via email to fix up a different time. What I would suggest is the four of you talk among yourselves and propose a couple of times for me, okay, that are suitable for you. We will try. Yeah. Their weekend and our weekend is different. So they have Friday, Saturday as their weekend. They work on Sundays. So we will work that out now. Don't worry about it. We'll work this out. Okay. As I said, I have only about 8 more lectures, and there are a lot of things I wanted to expose you to, ideas. So this phase of the course is going to be, it's not intended to, how should I put it? You need to know what the ideas behind are and how they are developed. So I will have all the equations and I will go through them, but focus on just getting the ideas, not filling the intermediate steps of how do I go from step A to step B, because if you want to do that, it will take us a lot more time. And so if you want to do that, you can do that outside of the class. So I just want to expose you to a whole range of ideas. Today, for example, in the lecture, possible I would like to finish the entire initial value problems. It's going to be tough, but I'm going to try. If not, maybe spill over to the next lecture. Similarly, one lecture for method of weighted residuals, okay, and one lecture for classification of partial differential equations, finite difference methods for partial differential equations, stability concepts and stuff like that. So I will try to give you an idea so that you can use these software with intelligence, and when you read the manual, you understand what they are talking about. So let me just quickly review. This is what I meant for the exam. You will find a box like the recap of previous lectures, and you understand what is in there, and you may need to review the lecture based on that. But any questions on that, you should be able to kind of discuss it, not develop the equations, but discuss the ideas behind that. So we essentially saw in the last lecture on finite difference methods, how to solve boundary value problems, ordinary differential equations, which are represented, for example, in the form a derivative operator operating on u is equal to f, which looks very much like an algebraic equation that we see, where A is the operator that operates on a vector u, which will give you a given forcing function f. But the path that we follow here is to do the discretization, and that is the key idea. Every derivative that we have in the D operator is replaced by finite difference approximation, and we reconstruct the matrix as the A operator, and then we solve that. If it is a nonlinear problem, then the idea remains the same. We discretize it. That means we put a set of grid points and we replace at every one of the grid points whatever derivative that appear in terms of its finite difference approximations. And that gives you a set of algebraic equations. You need to match the number of unknowns that you introduce at each one of the grid points with the number of equations. And there are certain variations that are possible in terms of the boundary conditions. The boundary conditions are the terminal points. Okay, and those are either the Dirichlet boundary condition, where the value is given, then it's quite natural and finite difference. You just impose the value. But if it is a Neumann or the Robin condition, mixed condition, then we also replace the derivative that appears in those boundary conditions by a suitable approximation to get an algebraic equation for that extra point. So when you have derivative, you don't know what the function value is, so the vector increases in size by 1 or 2, depending on what type of boundary condition that you have. And we saw how to do that in different ways, using a 3-word difference versus a sectoral difference, where we introduce a fictitious extra point. And then we moved on to look at specifically the convective diffusion equation. That's a key concept in here, because we recognized by solving that linear differential equation and comparing it, this is the finite difference representation for that. And we actually solved it analytically, the finite difference equation, and we found that there are two modes, just like the eigenvalues for the differential equation. The difference equation also has two characteristic roots, and one of them tends to flip sign if the Reynolds number is greater than 2. And that introduces an oscillation in the solution, in the finite difference solution, which doesn't exist in the original differential equation. That is what we will call this instability problem, a numerical instability problem. It's a purely numerical instability. It has nothing to do with the physical instability of the model. And so people come up with alternate ideas where you use this idea of an upwinding. Okay? And you should know what the concept of upwinding is. It's essentially to use a forward difference and a backward difference instead of a set difference for the first derivative that you see here. And it is weighted. It is weighted in such a way that I get an extra degree of freedom. The alpha, the weighting function, I can choose in such a way that I avoid that oscillation, spurious oscillation. So it does reduce the order of the error by 1, because the original one was of order h squared, but the forward difference is of order h. Okay, so it does produce a less accurate result, but there are other ways of handling for that, and of course to increase the total number of grid points. Also to redistribute your grid points in such a way that you have truncation error that are balanced, because the truncation error has two parts. One is the step size itself, the other is the derivative of the approximation. And in regions where the derivative is sharp, you put more grid points to control it. But in finite difference context, it's not as easy to put distribute the grid points as you like, and so this idea of algebraic grid mapping was introduced, where you have a mapping function to go from the original coordinate to a new coordinate. So all these concepts are very important. And there are whole books devoted just to grid generation, algebraic grid mapping. So it's a fairly extensive topic, but the simplest idea is to simply have a mapping function with some control parameters that allow you to adjust where you place the grid points. And so you have a computational grid which is uniform, on which you use the finite difference method, and a physical grid where the points are actually non-uniformly distributed. And this mapping is given by a function like this. Okay? That's the basic idea. And these ideas carry forward from dimension to 2 dimension to 3 dimension. And so from going from ordinary differential equation to partial differential equation, it's essentially an incremental addition of extra work, bookkeeping mostly. Okay? So that's the thing about finite difference method for solving boundary problems. We also discussed briefly about solving two equations, or also discussed briefly how to handle an infinite domain. Essentially, you still take a finite domain, but make sure that you gradually increase the domain size to make sure that you get independent results, domain length independent results. Okay, any questions on those? So I think I've been consistently doing this, so you should focus in preparing for the exam for the 15-minute part and be ready to discuss all those. Now, today I'm going to talk about initial value problems. We have already talked about quite a bit of the dynamical system theory concept, but we haven't talked about how the algorithms are developed. Okay, we've talked about using ODE 4.5 and other algorithms that are available in MATLAB, and similarly in COMSOL also has methods for integrating ordinary differential equation. We spent quite a bit of time developing algorithms for algebraic equations where we set this equal to 0. Okay, but now we are saying it is not 0, and so we need to construct a solution for y as a function of time. What sort of ideas are used in that? So this could be a vector equation, so y could be a vector of length n, and f would be a function. And if that function f has time in it explicitly, and that often happens when you have process control applications. Okay, so you want to externally control the process. So you have a time varying signal that you're manipulating the valve in a particular way over a certain time. So those are called non-autonomous systems. So a classification. Non-autonomous versus autonomous. So if that time doesn't appear there, then they're called autonomous systems. But if time is appearing explicitly, then they're called non-autonomous systems. What is the difference? The difference is our ability to translate the time. Okay, so if I don't have time in it and I construct a solution vector, okay, so I'm plotting y versus time, and the solution looks something like this, for example. Okay, now if this was the starting point, the solution looks like this. But if the starting point were here, how the solution look like? It will follow the same trajectory. Okay, so you can shift the time, because if you have dt, if I make the derivative of dt plus tau, tau is a constant shift, that remains invariant. But this function should also remain invariant, and that's the only way it can do so is if time doesn't appear. Okay, but if time appears explicitly, whatever the function value for the time has to be used, and so you will have different solutions at different times. It depends sensitively on the initial starting point in that sense. Okay, so that's a concept that you should know, but you can always, we will see two classes of algorithms today. One is called the multi-step method, the other one is called the single-step method. Okay, the single-step methods are developed for non-autonomous systems. The multi-step methods are developed typically for autonomous systems, but you can make a non-autonomous system look like an autonomous system through a simple transformation. Okay, so it's not really a big issue to make this distinction. There are physical reasons where it is important to understand, but from a numerical point of view, algorithms for class problems, it's not a very difficult challenge. So in the boundary value problem, when I had a differential equation, I knew what the boundary was in the independent variable. I discretized the domain, I converted that into a set of algebraic equations. Now what I need to do is, I still need to discretize it, but this is a time-dependent problem, so time can go to infinity. So I can march as long as I want, but I'm still going to be able to discretize it and get the solution only at certain times. I won't get a continuous curve. And of course, I can plot it using a plotting program. All it's going to do is connect the discrete values. So the algorithms will predict only discrete values in time. So the discretization is still there. So what are the types of discretization that we have? The first thing that we need to do is, there are two kinds of problems that one can face. One is a system of first order equations that I showed earlier. One is a single equation, but that is of high order. Okay, so here you see, for example, an nth order equation. Okay, how do I convert an nth order equation to be able to make it equivalent to a system of first order equations? Then I need to worry about only developing algorithms for system of first order equations, and that's what most of the software will do. COMSOL and MATLAB, etc. they do, and it's a very simple procedure. All you need to do is introduce a set of variables. For example, y1 is equal to, in this case, d theta dt. It's really not very responsive, so let me go to the screen here. And then introduce y2 as equal to, so sorry, y1 is equal to theta. Y1 is my big variable that I'm interested in solving that appears in the equation here. Okay? And y2 is d theta dt, and y3 is d square theta dt square, etc. So I'm going to define n such new variables, and so what would yn be? D to the power n minus 1 theta divided by dt to the power n minus 1. I don't know whether you are hearing me near the computer. So this is how I would introduce n variables, and I will then convert this equation to a system of n first order equations. Okay, and the process is very simple. Introduce the variables and then take the derivative of the first equation. Okay, when you take the derivative of the first equation, you're going to get dy1 dt. That is the same as d theta dt. That is the same as y2. You already get it, right? So that's going to be y2. And similarly, dy2 dt will be y3, etc. But when you go to the last equation, dyn dt, is going to be d squared dn theta dtn. Okay, so you move everything else to the right hand side, and you get your last function. So this is your first function f1. This is your second function f2. This is the last function, which comes from the ODE that you are given. Moving everything else to the right hand side and replacing d theta by dt with y2, etc. Okay, so you'll get a system of n first order equations like that. Questions on that? So what this tells us is, as long as you have an initial value problem, the key is for an nth order equation you will still have n conditions, but all those n conditions must be given at t equal to 0. Okay, then it's an initial value problem. If they're given at two different locations, then it becomes a boundary value problem. Then you'll use the methods from the previous lecture. So all we need to do is focus on how to solve a system of, I have it here. Okay, how to solve a system of first order equations. Okay, so this is how you would generate the boundary conditions, and here it is. Okay, I didn't realize I had the rows. So this is the definition for y1, y2, y3, etc. Okay, this is what I was just talking about. Okay, so dy1 dt equals y2, dy2 dt equals y3, etc. And the last one, dy1 dt, is essentially the equation where, except for d to the power n theta dtn, move everything else to the right hand side, and the corresponding initial conditions for each one of the variables. So now this is put in the same form as the equation that we started, system of first order equations. So that's what we are going to focus on. We'll solve system of first order equations. So what are the ideas in developing the algorithm? There are two essential ideas. One is the multi-step method, other one is called the single step method or the run method. Okay, so the first one is to understand conceptually, we're just going to use the Taylor series expansion. Okay, so remember, y is our unknown function as a function of time. So the equation is dy dt equals f of y. So we want to solve y as a function of t. So this has a Taylor series expansion because y, presumably f is continuous and so y is continuous, and we can do a Taylor series expansion like this. Okay. So we are organizing it. So y at tn plus h equal at tn plus y prime derivative at tn multiplied by h. So that's essentially straightforward Taylor series expansion. Okay. And we are saying, okay, now I'm going to truncate Taylor series expansion at this position. Okay, so I have a local truncation error of order x squared, but remember, truncation error is controlled both by the step size and by the higher derivative, which we don't know what it is. And if you look at this, what is left, it is essentially this. I'm changing the nomenclature on you. I call yn plus 1 is the next time step. So if the current time step, I can predict the next time step using the first part of this equation. So it's actually a very simple idea to grasp. Okay. Geometrically, what it is saying is, so if you give me for very first time t equal to 0, y0, I can predict what y1 is going to be, okay, at a certain time from that formula. Okay, so it's a purely predictive formula. So this will be called, so this is at 0, this is at 1, t1. The time step could be 0.01, 0.00, or whatever it is that you choose, but it's going to be able to predict that. How does it predict it? It simply assumes that the function is a straight line. And the function, what is the function? Function is the slope of y, because that is what the equation is. If you go back to the original equation, the function is nothing but dy dt. So by calculating the function, I'm calculating what dy dt is. And so I'm predicting what the next step is, assuming that the function is always linear between these two. And that's called the Euler scheme, which we used in Euler-Newton continuation. And somebody in fact asked me, is there a relationship between continuation methods and ordinary differential equations? The idea immediately that should come to your mind then is, in Euler-Newton continuation, we always stopped by taking the tangent vector projection. Can we do better? Can we take the next derivative of the function with respect to s, the arc length, and get even a better prediction? And the answer is yes. Okay. So this is the simplest algorithm, and it is called an explicit algorithm. Why is it called an explicit? These terminologies and concepts you should become familiar with. When you're reading the manual, you should understand when you would use explicit method, when you would use implicit method, etc. So this is called explicit method because knowing the current value, you can predict what the next value is using the linear approximation. The next question that you can ask is there a way I can improve the accuracy by getting a fit that is quadratic instead of linear, so that the truncation error goes from h squared to h cubed, for example. Okay, and it's possible. So it is that line of argument that we are going to see. Any questions on this? So it is a single step method because it needs only one current value to predict what the future value is. It's an explicit method because it doesn't need the future value. It predicts the future value knowing only the current value. An implicit method as opposed to explicit method would require you to iterate, okay, because you'll have the future value in your algorithm itself. So in this algorithm, whatever appears on the right hand side, it depends only on the current value. Okay. An alternate derivation, that was from Taylor series. But with Taylor series, if you ask the question, can I truncate it after the third term here and take this term into account? The answer is you can, but what do you need to do? That would be a question in an oral exam. What do you need to do? You already know the function, right? So what you need to do is take the second derivative of the function physically, because you know the functional form. You need to take the second derivative and plug it in. The problem with that approach is every problem is going to have a different function, so you need to take the derivative analytically every time. So we want a package which will solve any function. Okay, all I want to do is write the small function and then add it, and it should be able to give me the solution of varying accuracy, of very high accuracy. And that's the driving force of all these algorithms. So we don't pursue this idea further to develop higher order methods from Taylor series, and we ask, is there another method that you can use where I can systematically improve on the accuracy? And that method simply says, if you give me dy dt equals f, why can't I separate that out and write it as dy is equal to f dt and then integrate it? So convert it into a problem of quadratures, finding the area under the curve of a function. Okay. On the left hand side, when you integrate this from n to n plus 1, so we're going, it's all one step method, we're going from n to n plus 1, right? So you're going to simply get integral of dy is y, so it's going to give you yn plus 1 minus yn. On the right hand side, you need to find functional approximation for this function f. We already know how to do these things. We talked about functional approximation, right? So why don't we use, for example, a polynomial approximation in finding Newton polynomials? Okay, so Newton forward formula. So on the right hand side, then I take this formula and plug it in and evaluate the integral, and what I will get is a relationship between t and the new variable alpha. So the integration will be converted wherever I have dt, I will have h times d alpha, and the relationship would be t is equal to tn plus alpha h. H is my step size, okay, and I'm integrating from n to n plus 1. The reason that it looks appealing initially is I can truncate this at various levels easily, and then I just need to do the integration with respect to alpha and plug in the numbers, and I'll get a formula. So the question is, okay, what do I get if I take a one-term series expansion? Okay, so on the left-hand side, as I told you, I will get yn plus 1 minus yn. Okay, on the right-hand side, it is from tn to tn plus 1 of a polynomial of a certain degree. Okay, so here I'm using the 0th degree polynomial, and so the neglected term will be of order h. Again, it is integrated with respect to time. Okay, so and wherever I have dt, I have to replace it by h times d alpha. So the integration always gives you more accurate results because it smooths out the errors on up and as it goes up and down. So the error, the local truncation error, is of order h square, and the polynomial itself is, I said it's a 0th degree polynomial. What does a 0th degree polynomial look like? Just a constant, right? So we are saying the projection is that the integral is a constant. h d alpha comes from dt, and p0, the 0th degree polynomial, is simply the function. But we are integrating the function, so it is actually putting a tangent projection, if you like. Okay? And that gives you fn. And that is exactly the same formula that we had from Taylor series. Okay, so the one-term expansion of the polynomial gives you the same formula that we get from the Taylor series expansion with the same order of accuracy, which it must do. But the beauty of it is now I can say I have a method for systematically increasing the accuracy without having to take the derivative of the function. In Taylor series, I had to take that. In here, all I do is I do a polynomial fit and then do the integration. So I take next a first degree polynomial. Okay, the first degree polynomial will have two terms, fn plus alpha delta n. This is a Newton forward polynomial. Okay, and so the neglected term would be of order h squared, but it gets multiplied by h, so the truncation error is of order h cubed. Okay. Can I do the and notice another thing. I changed the limit from tn to tn plus 1 from 0 to 1. Why did I do that? Because I'm changing the variable from t to alpha. Okay, as t goes from tn to tn plus 1, alpha goes from 0 to 1. Okay, and that is from this formula that you have here. Okay, that's the relationship between t and alpha. So I can now carry out the integration and substitute the limits. So the first term would simply be constant, integration of constant is alpha. The second term is constant integration of alpha, which is alpha square over 2. But remember, in all these, the fn and the delta n are just numbers that come from the table that we extract, the difference table that we construct. So do the expansion for delta fn using its definition, and what you get is a formula that looks like this, h over 2 fn plus fn plus 1, with a better truncation error. Is it a single step method or a multi-step method? It is a still single step method because it requires the current step to predict what the future step is. So a multi-step method will require not only the current one, but the several previous values. And that's not natural for these problems because I cannot get started. When I start, I have only one value, right? So multi-step methods are not really meant for this kind of problems, but they have been used very effectively, and we will see how it is done later on. The second thing that you have to ask is, this is called the modified Euler method. Okay, the original one was called Euler method. It's called the modified Euler method. Is it explicit or implicit? If you look at the right-hand side, if you're going to now print this, what you need to do is, you need to evaluate everything on the right-hand side. Because you want to predict what yn plus 1 is, but I know what yn is, the current value. And I can calculate fn, simply plugging in yn. I'm trying to predict yn plus 1, so how would I estimate this one? How do I find out fn plus 1? That's going to depend on yn plus 1. Okay? So what would you do? you would treat it as a nonlinear algebraic equation. Okay, so it is like the method that we talked about, fixed point iteration. Okay, so you make a guess for your future yn plus 1, put it on the right hand side, and you get a new yn plus 1. Take that and put it back and iterate several times. Every time step, you need to solve a nonlinear algebraic equation. If it's a multidimensional system, n equations, you need to solve a system of n algebraic equations. So the amount of work goes up tremendously for every step. And this is the implicit method. The basic idea of implicit method is you introduce the unknown on the right hand side. Okay? And so you need to have a solution at every time step. Why would you do that? That's a good question to ask. Okay?
Because the errors don't propagate in an implicit method. If you've got an explicit method, every truncation area, every step you take, that error goes with it and it begins to build. Because you force it to converge, not converge, but you force it to match at each step. So
yeah. So the stability is the issue, because the errors accumulate and it can make the because you're going to repeat this to going from 0 to 1 to 2 all the way as long as you want, right? So you're going to repeat that, and so the errors that accumulate can make the scheme explode, even though the real problem doesn't have an instability, which you know how to solve those stability issues, right? So this is a numerical instability that we might encounter, and we will see a little bit about how to assess the stability bound of a method. So the explicit methods have a stability bound on the step size. If you take a too large step size, they might blow up. Whereas the implicit methods have the ability to predict what's going to happen and take that into account in the current iteration itself. So if I have a function for a problem, oops, what happened? For a problem where the solution y versus t looks nice, smooth like this, okay, the explicit method would be adequate. But if I have a problem where the solution does this, so there is a region where nothing is happening, explicit methods might be adequate. But if I am at this point, this is the same thing that you will see in the turning point kind of a problem, right? I mean, this point, I'm trying to predict what the future is. The solution is going down very steeply, but the explicit method doesn't see that. Okay? So the explicit method predicts what the value will be on here. Whereas the implicit method says, no, I need to know where the next one is, and it feeds back that information at every time step. Okay? So these systems are called differential equations, where there is a very short change over a very short time. Okay, it's an important concept, and we have talked about it in the transport phenomena course in boundary layers. Excuse me.
It's also really important with kinetics and reactor design.
It's important in reactor design, where you have multiple reactions, but one reaction is slow, the other reaction is fast. Okay? So you have two different time scales in which your variable is changing. That's called stiff problems. In the boundary layer concept, you have two different spatial scales on which things change. Near the boundary layer, the viscous forces are dominant. Outside of that, viscous forces can be neglected. The potential flow theory is adequate, right? So it's essentially the same concept, but the idea that these are stiff differential equations was probably introduced only in the 60s. The boundary layer theory was introduced in 1904 by Panford. And applied mathematicians have developed a whole field called singular perturbation theory, where things change in a different order of magnitude. But we need to recognize that some differential equations are stiff like this. Lorentz equation, for example, will have these kind of a sustained periodic causation, but over a very short time scale, it experiences a very sharp change. Van der Pol equation is another example of that. Sometimes they are called relaxation response or whatever. But in such cases, it is essential for us to use an implicit method. And of course, the amount of work involved is quite tremendous, so people have considered, can I do semi-implicit methods? And we'll talk about these ideas. So this lecture and maybe the next one is going to be just kind of covering these ideas and developing the algorithms as we go along. Any questions on that? So you should know what explicit versus implicit, single step versus multi-step, what step differential equation is, and the stability concepts we will cover pretty soon. Now, a question for you at this stage. I took one term and I got the Euler method from the polynomial approximation. I took two terms and I got the modified Euler, the implicit method. If I take three terms from that, what would I get? I'm not asking you to name a particular name. Such algorithms doesn't exist. So I want you to see the problem by taking more terms in that Newton forward polynomial approximation that we have. So let me put the equation here. If I take one term, I was okay. If I take two terms, I introduced, in addition to yn, I introduced yn plus 1 on the right hand side. How did that happen? Because I needed to expand delta of fn. What is delta of fn? Yn plus 1 minus yn. That's the definition for the forward difference operator. If I take the next term, this part I can carry out integration and substitute it. But I will get a delta square fn. What would that involve? Fn plus 2, Fn plus 1, and Fn. So I need to have two values ahead of time. So people abandon this because this is not going to work. If I continue to expand this like this, I have to solve more coupled problems. Assemble for one time step, assemble for the next time step. It's not going to be possible. What other ideas can you suggest that, based on what we have seen, that will allow us to improve and successively develop higher order approximations for this problem?
Have a feeder method that then feeds into that predictor. So it's not predictor correct.
The predictor corrector is a very good concept. I guess I should have probably talked about it, but that's not what the answer I'm looking for. Okay, so let me talk about, because I raised it. What is a predictor corrector method? So if I have an explicit method which predicts what yn plus 1 is, I mean I'm looking at modified Euler. Okay, where is it? Okay, the modified Euler method, I said I need to come up with a first initial guess for yn plus 1. How do I come up with a first initial guess? You can say, well, it's the same as yn. Same idea that we talked about in arc length continuation, right? That's a bad approximation. Can I do better than that? And the answer is, why can't I pair this up with an explicit method? So I predict my first prediction from an explicit method. Take that as the first initial guess, put it there, and then iterate on the implicit method a couple of times. So that kind of pairing of an explicit method with an implicit method is called a predictor corrector pair. So the predictor is the explicit method and the corrector is the implicit method, and you correct several times until it is converged to a certain tolerance. Okay. So when I say until it is converged, there are two issues that you need to understand, the sources of error. If you don't do enough iterations on this, the algebraic equation that you have may have an error. In addition, we have the truncation error that we need to manipulate by controlling the step size. So if you take small step size, you control the truncation error, and maybe the change is not sharp, so a few iterations of the corrector will get you to the machine precision for the algebraic equation. Otherwise, you will encounter round-off errors and errors because of incomplete integration iteration on the implicit method. So that's a good point. Thanks for pointing it out. So you can pair this explicit and implicit methods, and that are called predictor corrector methods. But what I'm talking about, yeah, here it is. Okay, so use the explicit method as the predictor, okay, and use the implicit method as the corrector, but the result from the explicit method feeds in, okay, and then you do the iteration on that. So this is true for, it's a general concept you can apply to any pair of explicit implicit methods. And what you will find is that the explicit method will always be one order lower than the corresponding implicit method. So you're actually improving the accuracy by applying the implicit scheme, but you're also handling the possibility of stiff differential equation. You don't know beforehand. When somebody gives you an equation and asks you, is this going to be stiff? There's no way you can tell, right? So you need to try out a few solutions. So going back to the, this is stability problem, but going back to that issue, how do I successively improve by taking the next term? I would like to get the answer out of you guys. Instead of me. I already laid out the concept. That is, if I take the next term in here, I'm going to need n plus 1, n plus 2. It's not going to work. But I can choose to replace this polynomial with I'm not ready for the oral exam. What are the other polynomials we have seen? This was a Newton forward
You can use a
polynomial.
Lagrange.
Newton backward polynomial. You can use Lagrange polynomials, but the Newton backward polynomial is exactly the same as this, except you have backward operators that require the current point and the previous point and the previous point, etc. Okay? So that will allow us to naturally expand it to higher order schemes by simply taking higher and higher order terms from that. And that's what gives you the multi-step method. For that, you need the current value and the previous value and the previous value, then you need multi-steps. And you cannot get, such methods cannot get started. So the strategy is you use the single step method to generate enough data and then switch it to the multi-step method. We need to what are the consequences of that. But before that, I think I had this notion of stability limits. We touched upon what the numerical stability is. How do we study the numerical stability? Suppose you are given this differential equation, the scalar equation, singular equation, and the function f is very simple, lambda to y. Lambda is your time constant, eigenvalues. Okay, and the initial condition is this. So immediately you can write down the solution. The problem is so simple that you know what the solution is. And so, question that we ask now is, and there are set of standard problems like this. Whenever somebody doubts a new method, they test it against those methods. This is one of the simplest of those test methods. The question you ask is, now I know how the analytical solution should look like for this problem. It should essentially be, if lambda is negative, the physical system is stable. If lambda itself is positive, then the system is unstable. Okay? So if the lambda is negative, then the solution should go like this. And what we are trying to do is put discrete points that approximate this from an equation like this, the explicit method, right? So does that produce the same behavior as the original differential equation, no matter what your choice for step size is? The error may be large, but is that behavior the same? Is the trend the same? That's a question we ask. So we can do that, answer that question just like we did for appending method. We can analytically solve this. For example, f in this particular case is lambda times y. So I substitute for f in terms of lambda times y. I can factor out the yn from there. And so the algorithm is the next value is equal to 1 plus h lambda times the previous value. That's a differential. So you can solve the differential equation. The differential equation will have a characteristic root, just like the differential equation did, right? But this is a first order differential equation because it relates only 2 points. A second order differential equation will relate 3 points, etc., just like a second derivative. So if I calculate y1 from my initial guess y0, initial condition y0, that's how I would predict for this particular problem, because I know f is h lambda. Then I predict y2 is 1 plus h lambda y1, but y1 is already known. So it is the same as 1 plus h lambda square y0. So what I'm trying to construct here is a solution where I can predict yn, not necessarily calculating all the previous n values, but just tell me what n is. If n is 30, I just plug 30 and I get what the prediction is. That is an analytical solution for the differential equation. And that solution simply becomes yn at any step is the same as 1 plus h lambda to the power n y0. So you give me the initial condition and you tell me what is the number of steps, I can predict what that is. The reason I do that is now I can try to put on that graph the discrete points that I will get. I'll draw the graph again here. So the continuous one, y versus t, was like this. And if you tell me if you tell me a step size, you need to tell me a step size because I need to put that in here. Okay? And lambda is coming from the problem. It's some constant in the problem. So if you tell me h is 0.1 and n is 20, I can plug in, and knowing the initial condition, I can put the point there and see how that behaves. Okay? As n goes to infinity. As n goes to infinity, what happens? T goes to infinity too, right? So I want to see whether this function will have the same monotonic decaying behavior that I get for my analytical solution. That's the key idea behind stability analysis. We want to see whether a numerical approximation that we have made has the same physical qualitative behavior as the analytical solution. We cannot do this for any general problem. Okay, that's why we restrict it to some test problems. So what do you think? The answer to that would be lambda is negative. I give you that because the physical system is stable. lambda, for example, is minus, okay, and h is 1. So what's going to happen? It will oscillate, right? Because I will get 1 minus 10 times 1, right? So minus 9, and as n changes, it's going to flip. So it's not going to be a monotonic decrease. Now, is it going to decrease at all? It's going to increase. That's a numerical instability. So if you pick in ODE integration, if you pick step size incorrectly, you can actually see the thing blow up very quickly. And that's a numerical instability. It has nothing to do with the physical problem because lambda is negative. How do I take control of that? I reduce the step size because that's something that I can control. So if lambda is 10, if I make my step size as 0.001, I'm fine, right? So it puts a bound on the stability. So you can then ask, for what value of h lambda would this be stable? What would be the answer for that question? For what value of h lambda, the product h lambda, what should be the bound on that so that you get the same monotonic decaying behavior? Or there are two issues, monotonic decaying behavior or a bounded behavior. If h lambda is less than 2, for example, it is minus 0.99 plus 1, so it's 0.99, so it's going to be decaying, right? But it's going to be oscillating, right? So if you want monotonic decrease, it should be less than 1. If it is one, if you want bounded response, you want it to be less than 2. And for stability, they just ask for bounded response. So h lambda, the absolute value of that must be less than 2 for this explicit method to be stable. And all explicit methods have a stability bound like this. And the book by Lapidus and Seinfeld has, the whole book is devoted to algorithms for ordinary differential equations. Develops a lot of these methods and then looks at the stability boundary for each one of those methods. It's a very good book. Any questions on that idea of stability?
Another one, still it's possible to oscillate.
This criterion, if you choose your h such that it's only less than 2, then it will oscillate, but it will decay.
Oh, yes.
It is stable. Okay, this guarantees stability, but not the same behavior as the analytical one. Yeah. Now let's try the same thing on the implicit method. Okay. So here I have the modified Euler method, yn plus 1 equals yn plus ho2 fn plus fn plus 1. But I know what fn and fn, fn is lambda yn and fn plus 1 is lambda yn plus 1 on the same model problem. Okay. And now I can factor the yn plus 1, combine it with this term, take it to the left side, and solve that. And what you will get is yn plus 1 equals this factor multiplied by yn. And the factor in square brackets is called the amplification factor, because you take the current value and multiply it by some number to produce the next value. And if that number is less than 1, you get a stable response. If it's greater than 1, you get an unstable response, right? So that factor was simply 1 plus h lambda in the previous case, but now it is 1 plus h lambda over 2 divided by 1 minus h lambda over 2. What is your conclusion? Is it stable or not for any step size that you choose? Lambda is negative. Keep that in mind. The original physics system is stable, so lambda is negative. So here I will have a 1 minus h lambda, but lambda is negative, so I will have 1 plus some number, no matter how big h is. It's 1 plus some number. The numerator, it becomes 1 minus the same number. So that ratio has to be always less than 1. So this is guaranteed stability, no matter what the step size is. It doesn't guarantee accuracy, but it guarantees the same response as the original system. All implicit methods share that feature. Okay? Because they have the ability to anticipate what the sharp change is coming, they can produce a stable response, the same stability as the physical system. Of course, if lambda is positive in the original system, you would expect the numerical approximation to capture that, so the numerical method also blow up. So the key thing is, when the numerical method blows up, you're doing it for the first time, you have a model, you're programming it, and you integrate and it blows up, you won't know whether it is caused by physical instability or numerical instability. Okay? How do you address that question?
Implicit, use implicit to see if it is caused by the
because you know, well, this proof is only for a model problem, right? So what this tells us is implicit methods have better features than explicit methods. It doesn't mean that it will work for every problem. That's a good suggestion. You can try it on implicit method. okay? And it will allow you to take larger step size. Reduce the step size and see whether you can make it remain bounded, okay? So the grid independence test that I'm talking about in your project, whether it is spatial or temporal, is a very important one to make sure that only when h goes to 0, you recover the analytical solution. The numerical solution approaches the analytical solution in an asymptotic way as h goes to 0. So you must do the grid discretization at least at two different levels. If it is time-dependent problem, different time sizes, spatial problem, two different grids, one finer than the other, and see how much of a change it produces. And you will see that the change that it produces becomes less and less as you have finer and finer grid. So this essentially shows you how to get the final solution as relating any time step n to the initial time step to the power n. And we just said that this factor has to be less than 1 stability, and it will always be less than 1, no matter what step it is. So there is no stability bound on the step size for implicit method. So what is a stiff differential equation? This is something that actually I used in the previous course, transport phenomena course. It's essentially a spring and dashpot model. It's any second order ordinary differential equation. Stiff systems, you need to have at least two different time scales. That's the point that I'm trying to drive at. If you have 100 you can still have stiffness in that, because the stiffness is a measure of the ratio of largest eigenvalue to the smallest eigenvalue, because eigenvalues are the time constants, the time scales in the problem. For a nonlinear problem, these time constants are not constant forever. For a linear problem, once you solve the characteristic root, it's constant. It's not time dependent. For nonlinear problem, it can change. The Jacobian changes, and the eigenvalues of the Jacobian are the ones that determine this time constant. So the idea again of a time constant is easy to understand when we look at a linear problem with C, K, and M as constants. But in a nonlinear problem, you will know only when you see a sharp change in the profile with time. Okay? The solution for this one is given by this particular function. And there are two components. One is e to the power minus kt over m that you see here. The other one is e to the power minus ct over k. I don't know that PI guys may not have seen this. Those who have done the transport phenomena course from me will know that this model comes in many places in electrical engineering, RLC circuit, etc. But this is the one that I talk about, where you have a mass that is controlled by a spring and a dashpot. If you make a force balance on that, you will get that particular equation. And when you plot the full solution, you will get the solution that I had. You will get a profile like this. Okay, but so there are two parts. The first part is the outer one is the slow solution from this point on. The dashed line is the slow solution that we get by assuming that m is small so that I can neglect the mass. Then when I do that, I will get a first order equation. So I go back and I say if m is too small, then I can neglect that and I will get a first order equation and I will get a solution which is good for over long time, but it is terrible for very short time initially. Okay? To solve the initial one, you need to keep this. And look at this, what happens to this term, the fast term. If m goes to 0, kt over m, because m appears in the denominator of the exponent, it's going to go to 0 very quickly. So the fast solution will lose its impact on the total solution over a very short time. And then it's okay to neglect that. But not in that small time. Because even though m is large, when m is 0, for example, approaching 0, there is a place where time is also 0. That ratio is still significant. Okay? And that's what the essential idea behind stiffness. You have two time scales in the problem, and they manifest themselves in the form of having a very rapid response over a short time. And if you take a large time step, a time from here to here in one time step, you're going to miss that part. So in stiff regions, you must have small time steps. Okay? And so that introduces the idea of variable step methods. How can I change the step size so that I can adapt? In slowly varying region, I can take larger step size. In rapidly varying region, I must have smaller step size. It's also an idea that we talked about in continuation methods in the parameter. Right? So there we just used a simple idea of a ratio of the number of iterations. Here we need to look at we need to assess how fast the solution is changing, and there are some ideas for doing that using what are called embedded methods. We'll talk about maybe in the next class. I'm running out of time. But let me just continue with this solution. So, I mean, you just saw the characteristic equation for the particular problem, and these are the two characteristic rules. When m is small, this term is very large. And typically the stiffness ratio is defined as lambda 1 over lambda 2, or lambda max over lambda min in a multidimensional problem. And if that ratio is more than 100, you typically call such systems as stiff systems. These are very ad hoc guidelines. Remember, these eigenvalues are not going to be constant for a nonlinear problem. So it may appear stiff in one regime and it may not be stiff in another regime. Okay, any questions? So in this particular problem, the stiffness ratio is k squared over mc. So you can achieve a large stiffness ratio by manipulating all these numbers, but it is easiest to think of, at least for me, m being the single parameter that I control. And if you remember from the other course, I said consider two such systems. One is with steel ball, the other one with the styrofoam ball, and you perturb them. What will be the response that you will get? The steel ball will oscillate. The styrofoam ball is going to snap back, to controlled by the spring and the dashboard. So we are touching upon a lot of these concepts. Let's go back to multi-step method, where we left off with that idea of replacing the forward difference approximation by a backward difference approximation. So these are all the backward difference operators. The same function is approximated by a polynomial. The function is the one that is given in the problem. It's exactly the same idea. All I'm doing is using a different approximation for that. So if I take, for example, a second degree polynomial, okay, and so I'm going to take 3 terms in there from the back difference. Okay. Now if you take the first degree polynomial, what do you think you will get? The implicit modified Euler method. Okay. So if now I'm trying to expand by taking one more term in that, and what I've done, the truncation error, local truncation error is about an h cube that gets multiplied by h, so it goes to h to the power 4. That's a very so if h is small, for example, I can achieve very great accuracy by simply taking an additional term in the series and developing the formula once and for all. And so now all I need to do is integrate from 0 to 1. Integration is with respect to alpha, and I can substitute for delta fn and delta square fn. But the integration, watch, integral of alpha is alpha squared over 2. Integral of alpha squared over 2 is alpha cube over 3. And alpha is alpha over 2. Just term by term integrated. And substitute the limits 0 to 1. And then substitute for delta fn. Definition of delta fn is fn minus 1, because it's a backward difference. And the definition for delta square fn is fn minus fn minus 1 plus fn minus 2. So this formula demands that I have values before I can predict what the next value is. Okay? So it's not suitable, it's not a self-starter. I cannot use it until I use other method, the modified Euler method, maybe generate enough information. But the reason that it is attractive is its truncation error. With just one additional function evaluation, I get the order to be much accurate. Okay? And this gave rise to the so-called variable order methods, Gear method, Adam-Bashford method. There's a whole class of algorithms that are based on this idea. Systematically, it can be improved. So this is a 4th order method. That's the final result. And you will see formula tabulated like this, and then algorithms that you need to write. So all you need to do is one line and put a loop around that using constant step size, and make your function a separate thing. So you write a function that defines a problem, and you call it to this function. This function integrates. Exactly what ODE 4.5 does something similar, but it's a paired method also. So I'll talk about it later on. Okay, any questions on this? Yeah.
So we're doing like boundary value problem, or sorry, initial value problem, where we're kind of using we use previous methods to kind of get the new values, and
Yeah.
we use essentially this method to predict further values
Yeah.
there. I understand all that, but is there? I see our local error is h4 essentially.
Yeah.
But our global errors depend on the error of the previous solutions.
Yes, yes,
That's
Yeah.
Is there a way to judge how close you are in terms of like, by you? I mean, I know essentially our global errors can be restricted to the initial guesses at that point.
Yeah, yeah.
I mean, you could be more accurate, but we could be predicting over something that's
Right. That's an important point. The global errors always accumulate. Okay, and the only way that we have to control that error is through step size. Okay, so the question then is there a way to estimate what the error is in the solution as I march along so that I can adjust step size? Okay, and there are essentially two ideas there. One is for these type of methods, estimate the solution using two different step sizes. So use ones with step size of h, another one with step size of h over 2. So you have two predictions and see how different they are. And if they are agreeing to 4 significant digits, that means you have 4 significant digits and that's your acceptable tolerance. That step size is okay. Now if this is 10 to the minus 8, the difference is 10 to the minus 8, then you say, I can take a bigger step size the next time. So you try twice the step size. Okay. So either you double or half. But estimate 2 using 2 step sizes every time step. It looks like it's a lot of work, but these computers are very fast, right? So those are already implemented in a lot of freely available programs. You can actually download these programs. Lawrence Livermore Lab has a package called LSODE, and they are very powerful packages based on multistep methods like that with variable automatic step size control. The other idea is related to single step methods, where you build 2 formulas that use exactly the same information except for one formula has an additional information. And so you get 2 predictions, and they differ also in the order. One will be of order h cubed, the other one will be h to the power 4. Okay. Here they are all both the same order, but you're using different step sizes to get the error. There you have 2 different orders embedded in other. So the additional work is lower, and when you see the method, you will understand how that works. And so in all these cases, you need to estimate what the error is in the next step, either by controlling, doing the repetitions with 2 step sizes, or cleverly constructing the formula. RK45 is one, which is cleverly constructed as an embedded formula. Okay, that's a good question, a very good observation. So that's what I want you guys understand conceptually. You can, if I give you an assignment, I know you struggled with number 2 and you did it and you understood how it works. So if I give you an assignment on this, you will really understand the nuts and bolts of it. Okay, but we don't have the time to do that. So all I'm expecting is you have proven that you can do it. I know that you can do it for every problem that we have talked about, but get a conceptual understanding so that when you're using the software, you can do it with some smarts. Okay, that's a basic driving force for this course. Okay, so this is not a self-starter, and because it requires previous values, and when I start, I have only one value. Okay, and this is an explicit method. How do I know it's an explicit method? I look at on the right-hand side. I'm trying to predict yn plus 1. But all I need is yn minus 1, yn minus 2, all or no. If I get in there fn plus 1, then it will make it an implicit method. That method will be suitable for stiff systems. This method is not. This method has a stability bound. What is stability bound? It's not h lambda equals less than 2. Maybe it's h lambda less than 3 or 4, slightly larger stability bound. The process of obtaining the stability bound is exactly the same. Take that model equation. What would happen if you take the model equation and plug it in here? You will get a difference equation. What would be the order of the difference equation? If it involves n and n minus 1, it's first order. If it involves n, n-1 and n minus 2, it's second order. You have 2 characteristic groups. It involves n, n minus 1, and n plus 1, n, n minus 1, and n minus 2. So it's a third order. So you'll have 3 characteristic groups coming from that. You can solve it using the same method that we've seen before. Okay, so it is not suitable for stiff differential equations. Any explicit method, you can state that it is not suitable for stiff differential equations because it can anticipate sharp changes. So implicit methods typically will not have a stability bound. You can use any step size, but the methods do have that. And it requires only one additional function evaluation every step, but still you get extremely high accuracy. That's the main advantage of this. What do I mean by that? If you're calculating yn plus 1, you need to calculate fn. Function calculation is the most expensive part in this one, right? And fn minus 1, fn minus 2 has already been calculated before. just to make sure that you have storage space for them. You store it so that you know calculate it again. Then an additional function evaluation gives you h to the power 4. Now you can see, why can't I develop that method of order h to the power 5? All I have to do is go back, take one more term. It will require, instead of n minus 2, n minus 3. So before you can start using that, you need to accumulate maybe 3 steps or 4 steps. And this is the idea behind the variable order gear algorithms, where they change the order as you continue to integrate, as you accumulate enough information, change the algorithm that you are using to get more accurate result for one additional function evaluation. Yeah, I guess I did throw in that one too, right? M equal to 3, so you take first 4 terms in the series, and you will get a formula that has n minus 3, n minus 2, n minus 1, and n. Still an explicit method. It has a finite stability bound. And these are the ones that are done very well in the book by Lapidus and Staples. If you want to know what is the stability boundary for a particular method, just go in there and you can look it up and see how it's done. I guess we're almost out of time, so maybe I'll stop here. What do we need to do? The next question we need to ask is, what do we need to do to develop an implicit class of methods that are also multi-step? That is, how do I introduce n plus 1 on the left side? Okay, maybe we'll pick up that on Wednesday, and then hopefully this section by Wednesday. Any questions?